So today we are learning about the inputs. So we all know that we in our last previous class we understood that what before us what they like others what they do and after what they do. So we know that, and we know we also know the inputs. Okay, but we should also understand like what like inputs, what does it contain, what does it contain. We should also know that. Okay, today let's try to understand the inputs. Okay, so basically for a PD engineer, for being a PD engineer, he needs certain inputs. First is netlist. Okay, netlist. These are the very like minimum inputs to get start with the PD flow. Okay, in netlist and .lib libraries. Next, and lefts lefts and SDC. So these are the four minimum inputs. I am again repeating. These are the minimum inputs. Interviewer asks you what are the basic inputs you need to start the PD flow. Okay, so at least you should able to tell these 4 points: netlist, libraries, left, and SDC. Okay, okay. Let's start. What is netlist? Okay, so we just I just told you like netlist is it contains the logical information. Like what? It contains the input and output information of the design. Okay, keep these points. I think you better by heart these points, because interviewer definitely this is a very basic question they will ask you. Okay, I recommend by heart. Literally, you by heart these points. If someone wake you in the midnight, also you should able to tell these points. Okay, netlist, what it contains: input and output information of the design. I'll tell you what is input, what is output. Like let me draw one block. This is your block. So you will have the IO ports, right? So and you will have output. Maybe these are output ports. Also, you will have the input ports. And let's say if you take one cell, so this is input and this is output. So this like this kind of information it will contain, like where this pin, where should it connect. So that kind of information it will have. I have the netlist file. I will show you later. Okay, so you understand like netlist will contain the input and output information of the design and the wire information. Okay, wire information, like let's say you have one inverter here, and okay, let's say this is the wire. So it has, this is the pin here, and these two pins get connected with the wires. Okay, this is we call wire or net. Okay, this is wire. So this kind of information also netlist contains. Okay, then cell and instance information. Cell and instance. Okay, what is the cell and what is the instance? Let's say I have one logic A plus B equal to C. So this logic being used many places in my design. Okay, let's say this AND gate is performing this function. Let's say, okay. So they will define only once. Means they will create this logic only once, and that one logic we called as a cell. We will call as a cell. Okay, SELL, cell. So we will clone them, clone this logic. The cloning logic we call as a instance. Like this again, we don't need to build, right? Once you implement this logic, you can just clone it. Okay, this is instance. We call as a instance. Like let's say this is cell 1, So cell, then we call as a cell 1, cell 2, any number of times we can use it. Cell n, sorry, yeah, this we call as an instance. So that kind of information it will have, the netlist will have. And the module information. Module information. Module is nothing but like it's a collection of the logic, like uh, like the module, like it contains a lot of uh, logics. The module, like one module, it consists of a lot of logics inside. So where should sit that logic in our core area? So that information it will have. I'll show you the netlist file later. You will clearly understand. But for now, just remember these points. Okay, module information and the hierarchy information. Okay, hierarchy is nothing but like we will the full chip, you know, right? The full chip, and we will do some partitioning. So it's a hierarchy. Like they will sub partition. They will give it to you, and the hierarchy is like nothing but like A B C. Let's say that's one instance name like ABC slash DEF slash like that. So whichever like you, if you see the slash, right, so that is the hierarchy name. Okay, the port information, port information. So this port information. Okay, so these are the like minimum basic points I just mentioned. So at least you should understand and you should remember these minimum points. If interviewer asks you, you should able to tell these minimum 6 points. Like you should tell like we will have netlist, libraries, lefts, and SDC. SDC like it's a synopsis design constraints. But yeah, it's a general, you can say also constraints file. Okay, there's minimum 4 inputs we need, and the netlist contains input and output information of the design, and the wire information, and the cell and instance information. Okay, cell and instance information, module information, hierarchy information, port information. So is this clear to everyone?
Okay, sir.
Your voice is not clear actually.
Yes, it's clear.
Okay, good. Okay, next let's check the .libs, .lib library. Okay, so library it contains the it will have the timing information and power and functionality of a cell, like particular cell what functionality it has. So that kind of information and timing information, like if you are if you are using a buffer, or else let's say AND gate, so each pin will have the certain timing information, like uh, I think let me show you. Okay, okay, so each cell will have the timing information. Let's say this is AND gate. So this arc, right, we call this as a arc. Let's say A, B, C. So this A to C, this arc. So this each one will have the timing information. So that information, the library will contain this kind of information. I think you guys already know the input, the transition time, right? Like uh, I think before that, let me explain the cell delay. Okay, let's say this is a cell, this is a buffer. Okay. So the buffer, any cell in our design. So the delay depends on the input tran and output load. Okay, it's an interview question. Cell delay. Maybe interviewer ask you like in what like what are the parameters, like the cell delay depends on which parameters. You should tell like the cell delay depends on the tran input tran means like the transition input transition time and output load. So cell delay depends on the input tran like this and the output load. If the buffer is driving some other cells, let's say one more AND gate, here one more AND gate. So the fan out is here two, right? The buffer is driving two cells. So that's why the cell delay, it depends on the input tran and the output load. We will have one lookup tables. So we will get, the tool will pick the, based on this tran value. Like maybe let's say this is 2 PS. Okay, let's say this is 2 PS and the cap is maybe point 4 femtofarad. Okay, femtofarad. So there will be lookup table 2 PS and 0.4 femtofarad and this much is the cell delay. So that information lib will .libs will have. I will show you in the file. Okay, so basically the input transition, interviewer also will ask you what is the input transition. So input transition is the time taken by signal to reach 20% to 80% of a peak value. That is the rise signal. Okay, rise signal 20% to 80%. Or we will have rise and fall, right? This is rise and fall. Okay, this is the rise and fall. So what is the rise time is like the time taken by signal to reach 20% to 80% of a peak value is a rise signal, and it's like a reverse in like to reach 80% to 20% of a peak value is a falling signal. Okay, that is the rising signal and falling signal. Output load is nothing but the total capacitance value that is connected to the output pin of the cell. So the total it will calculate the total capacitance value. Okay, it will you don't need to do manually. It will be automatically get calculated by the tool, and it will go inside your library file and it will select the delay value. Let's say so let's say this is tran. Okay, tran, and this is the cap. They will give some delays. Maybe just now we thought like this is 2 PS and maybe this is 0.4 femtofarad. Then maybe the delay may be 20 PS. Okay, this is the 20 PS. So tool will pick this delay and assign that delay 20 PS to this cell. Okay, and okay, next it also contains the power and leakage, the power information like leakage power and internal power, and also the cell functionality. Okay, the cell functionality and the PVT conditions. I think the cell functionality is, I think it's you guys know, right? It's just functionality, like what the cell does, what is the functionality, and that information also it will have. PVT is like process, voltage, and temperature. Okay, process, voltage, and temperature. Okay, the PVT stands for process, voltage, and temperature. Like what is PVT? Okay, So you built one chip. Let's say you built one chip which does the a plus b equal to c function. Let's say this whole chip performs a plus b. You, let's say, like the end user, the user give the two inputs, like 2 plus 2. He will give the two inputs, a value, b value, and the outcome should be the 4, right? So this is the function of this chip. So this chip should work in every place. Like if let's say you implemented this chip and you release the chip and it is just working in India, not in other country. So it doesn't make sense, right? So the chip should work in all the weather conditions, like the coldest place, Antarctica. Okay, I think it is around minus 80 degrees, I think. And also the hottest place, Arab countries, Maldives. So there will be around 27 or 20, like that. So the same chip should work in all the weather conditions, like rather than in single temperature and voltage, it should work in other all varieties of temperatures and voltages. So that is the PVT conditions. So this PVT, like they will give some zero point 0.5 volts, like low VCC. They call this is a low VCC in real time, low VCC, and point maybe 1 volts. This is the high VCC, high VCC, and zero point 0.8 something. This is a mid VCC, mid VCC. So in all voltages, so they will verify this chip is working or not. If it is not working in any other voltages, they don't. I mean, they don't print this on the wafer, silicon wafer. So that kind of PVT conditions also lib will have. Okay, so you guys understand, right? Like what lib having. Okay. Next, is anyone having any doubt?
No, sir.
Okay. Next, dot left. Okay, left. Left stands for library exchange format. Library. Okay. Let's see what left contains. So it has the physical information of the design, physical. Okay. Physical information. Let's say you, okay, let's say this is your chip, and maybe let's say one buffer is sitting here. So it's physically you are seeing it, right? So physically, so the physical means what is the height of the cell and width of the cell, what is the orientation, like all this kind of information you will get in the left. Okay, so basically these are two types actually, technology left, tech left, and cell or macro left. So you should know, like, left, what is left? Left is a library exchange format, and it contains the physical information of the design. So in our design, in the left, we will have the two kinds of left. One is technology left, and the other one is cell left or macro left. Okay, let's see what is the tech left. Okay. Okay, it's okay. So the tech left is like it contains the metal information and the VI information. Metal and VI information. Guys, like while I'm teaching you guys, you try to note down some points. These points. These are very important. Okay. So the tech left is contains the metal information and the VI information. What it means? Okay, let's see. So you have an AND gate. Okay. Okay. Okay, it is connected to one buffer, let's say. So we already know the horizontal will be, let's say, M2, and vertical M1, and this is M2. These are it connected with the metals. Okay, And there will be via. So this is a contact point. We also call it as a contact. This is the contact via. So with this via only, the connections you will see. Other, if you don't if you don't see the via, right, this will be a open. Open is like it comes under L or this LV guys. So they will catch this and ask you to drop the via here. Okay, so this kind of information the tech left will contains the technology left, the metal information and via information, like what type of via it should drop here, and what type of like what type of metal it is. Okay, next. Uh, okay, we metal, right? Okay, let's see metal. Like what kinds of like what is metal? Like how much width and how much like we will have a lot of metals, right? Like yeah, from M0 to M0 to M15, let's say. So what is the difference all these metals will have? Okay, let's see. Metal. So metal basically, oh yeah. So metals will have the direction. In the in this left only you will see all this, but I'm like telling you like in a sub points, like the basically you should understand left will contain the physical information. Okay, what kind of physical information? It will have the tech left and the cell left or macro left. Okay, in the tech left now we are knowing about the tech left. Okay, in the tech left we will see the metal and via information. Okay, then metal, what metal is, like what kind of information metal having. Okay, that is we are going to talk about now. Okay, direction, metal direction, like it is horizontal or vertical. Next, picture. Each metal will have some pitch, like the distance, how much, like let's say you okay, you routed like this, and again one more buffer is here, which again driving like this. So this distance, the spacing will be there, right? So this spacing will be given here in the left. How much, how many microns? Let's say 1 microns. Okay, 1 microns. So this kind of information, the picture. And the width. The width will be different for each metals. The more, like from the more you go for higher, right, you will, the width will be more. Okay, width and area and min enclosure min enclosure and capacitance and the thickness of the metal. And yeah, I think these are the basic information metal will have. Okay, let's see via. What is what via contains. Okay, via. Okay, so via is spacing, via to via spacing. Okay, and the width, via width. And I think antenna, like one antenna information. I'll tell you later this. And antenna model like this. And next, cell left. Okay, cell left, cell and macro left. Okay, so cell and macro left, it contains the class. Okay, what class is, let's say we know that if you see like a square box, a big square box, we understand that it is a macro. Let's say this is your, if you open the floor plan, so at the bottom here somewhere the tool will place here. Okay, some very big square boxes, that means those are the macros, which MACRO, macro. or also we call as a SRAMs macros. SRAMs are hard macros also. These are also we can call as hard macros. So how does tool know it? We know it by the visually we are seeing it and we are saying it a macro, but how tool know? So tool for each and every macros there will be a attribute called class. If it is like I think it will be block. I think some I don't recall. Maybe it's a block. I think so. For macros, the class attribute set to block. Okay, if it is seeing the block, that means it's a macro. So that kind of information it will have class information and the origin. Okay, origin means the what we say like maybe orientation, like we will have our 180 degrees, sorry, 180 and or maybe it depends on the project. Okay, you don't need to worry about this, just to understand like what is origin means, like the origin means the orientation, or in which angle you want to turn the macro. And yeah, so that kind of information, it depends on the project and company, they will change these orientations. Okay, next is the size of the macros or cells, and the symmetry and yeah, I think only this. Lefts will contain the physical information, and also lefts are two types: technology left and cell lefts. Inside the technology left, it contains the metal and via information in the technology left. Okay, and inside the metal we will have these information: the metal layer direction, pitch, width, area, min enclosure, and capacitance and thickness. Okay, next via information is like spacing, via to via spacing, and width, via width, and antenna modeling information. Okay, and then the macro or cell left, it contains the class information, origin, size, and symmetry. So please remember these points. If anyone asks you, you should be able to tell this. Okay, you understand, right?
Yes.
Okay. Then SDC. So SDC is nothing but like it's a constraint related information, like the clock definition. Okay, clock definition. And clock definition is like what is the uh, time period, frequency, and waveforms. So all that information in HDC you will see it. We will go through that later. Okay, and yeah, create clock information. Create clock. There is a command called create clock, which creates the clock actually. With the we will mention in the create clock dash name, the clock name and the period and the waveform, all that information. Okay, and the virtual clock, and uncertainty. We discussed in our STA uncertainty, right? And external delays, and IO input delays, and output delays. Input and output delays are like let's say this is your full chip. Okay, they did some partitioning like this, and like A, partition B, and C, and D. So let's say you have been assigned to this partition. So they will give this IO ports. Okay. So each IO port will have some delays. In, let's say if it is a output means it the output delay, and input means input delays. Okay, this kind of information, like let's say one AND gate is here, it is going through this port to here, one more AND gate, let's say. So how much delay they having here? Or let's say you have been given 500 PS to meet the path, and if this partition using already 500 PS, you have nothing to I mean to do optimize. Let's say you will route this, and you will get some RC delays, and you need to buffer to fix the tran violations. So and in that process you will see some delays. So if they don't give you any like some delta to you, then you will see timing violations. That's why they will do some budgeting. We also call as a budgeting. Remember this word, budgeting. Top level guys, they will do it. Okay, budgeting. So uh, they need to use only maybe 200 PS. Only 200 PS. If they use, you will have another 300 PS. So that 300 PS you can use for your optimization. You can route. You need to route it, and you need to buffer it to fix the trans and all. So if you are within the 300 PS, then you are good. Your timing path will meet here. So this kind of input delays and output delays will be provided in the SDC. And max tran, what is the max tran and max cap? I told you, no, each cell delay depends on the cell delay depends on the max tran and max cap, right? So of course, if you consider this as a cell and this is also one more cell, so you should be given the max tran and max cap. You should not uh, cross that. If you're cross that max tran and max cap value, then you will start seeing the max cap and max tran values, which again impact the delays. So that's why they will give you these constraints. Your tran should be within this, let's say 2 PS. Your cap should be within 0.4 femtofarad. So they will give this kind of constraints. So you will get these constraints from clock team. Mostly the clock team will give it. Okay. Next is the timing path exceptions. Timing path exceptions. Timing path exception, like it's like is it false path or multi-cycle path, or else half cycle path. We discussed in our STA class, right? False path we didn't discuss, but I explained the half cycle and the full cycle and the multi-cycle. I draw one like this waveforms. This is the full cycle. This is one full cycle. If that path captured here, it is a full path, and if it is let's say if captured here, it's a half cycle path. And if some paths maybe some paths need a multi-cycle path like this, maybe it will take 2 cycles. This is one cycle, and this is one more cycle. So these are the multi-cycle paths. So this kind of information also you will see in the SDC. Okay. And max delay and min delays. So yeah, just remember these points. If anyone asks you, right, you should able to tell some at least some points. Okay. So you understand?
Yes.
Okay. Then let's see the lefts first. This is the left. Okay. Don't take any snapshot. Actually, these are confidential file. I got it from somewhere else. So don't take this. Don't take any snapshots. Okay, let's check the left, sir. Just know what we discussed here. Left. Okay, left will contain the physical information of the design. This is the complete all metal and cell related information in this left only you will see. Those are I merged everything in this one file. So yeah, but in the real time, like you will be given two kinds of files, like tech lefts and macro left, and yeah, this SLF or macro left, and one other is tech left. Okay, let's see. So tech left, it contains the metal and via information. So metal will what metal contains? The direction pitch, right? Let's see here. So yeah, this is the defined here, the layer and metal. You can call as layer and metal. It's nothing but same. So this is the metal one. So in this project, like our metals get start from one. Sometimes like in the other projects, some other companies, they start their metals from zero also, metal zero. Okay, and so see here width, the metal one width, how much it is? 0.230 microns. Okay, this is the width. Spacing, okay, 0.230 spacing, the metal to metal spacing. If you are using M1 metal, I explained here, right? So this, let's say this is M1, the spacing between here, so it should be how much here they're telling? 0.230 microns, the spacing between two M1 metals. Width should be the 0.230. Like width means the width, it's a normal terminology, no? Width, this is the width. Let's say this is M1, this is M1 metal, this is the width. It should be 0.23 or something. So this is the width, the M1 metal width. Okay, and the spacing, okay, maybe pitch 0.560 pitch. Let's say you will be given some more tracks, right? Okay, in the floor plan, I'll explain you what is track and what is rows and all. So let's say, okay, this is your partition. Your whole partition will be covered with these dotted lines are the tracks. Let's say these are some dotted lines. So the tracks will help you the tool to guide the routing. Okay, like let's say here M1, you routed like this. This is M1. So from this track to this track, this is the picture. How much is the distance from track to track? That is the picture, 0.560. And the direction, let's say here is the horizontal actually. But so far we learn is if it is a odd number, it should be a vertical, right? It depends. The process is different. It depends on the project. In this left, they're saying their M1 layers will be in a horizontal. Okay, and resistant numbers and the cap related information, this one. Okay, so and here some antenna related, the thickness, we also learn the thickness, right? How much the thickness of the metal. And yeah, the definition is end here, the metal one definition. Okay, let's see the VR2. So each metal will have the VR information. Let's say you connected one cell like this. Okay, there is one buffer something and one more buffer here. So you will connect here, right? You will drop the VR obviously. Okay, so this VR information also you will see here. Say via 1 2, 1 means metal 1 to metal 2. Let's say the naming is okay, you don't worry about this naming, but you should understand like what metal information you are seeing, like type cut and antenna area ratio and antenna difference area ratio. So basically like VI is like spacing, width, antenna information you will see in this in here. Okay, and the metal 2, now metal 2 definition started. Metal 1 is finished and the metal 1 VR, this is the metal 1 VR related information. Now here metal 2, same information like type and width, you see here width, how much the metal to width. I think metal to the more higher metals you take, right, the width will slightly increase. That means that means what, resistance will get decreased. If resistance is getting decreased means you will see the less delays. So that is the point, like they will give all these kinds of metals. Let's see, this is the width 0.28, right? Let's see whether see here the metal one width, if you see here, right, 0.230, and this is slightly bigger than the metal to slightly bigger than the metal one, 0.20. So the reason is like they want, if you are using metal 2 means, let's say if when you are using metal 1, if you get some maybe 2 ps of delay. Okay, okay, let's say this some cell is here, you connect it like this, and I told you this is one metal 1, right? Okay, this metal 1, maybe this is giving zero point 0.2 ps picoseconds of delay. But if you use some metal, this is okay, let's say this is metal 1, maybe metal 3, if you use metal 3, maybe this will go down like maybe 1 ps, because the width is high. So the resistance will decrease and the delay will get decreased. And the spacing is 0.280, means spacing should be the same. Spacing is also different, metal to metal. And yeah, you see the pitch, this is the pitch 0.660, here 0.560. It is also different. Each metal to metal it will get vary. Okay, metal to each metal to metal. And the direction you see here, it's a vertical here. Now it's even. 2 is the even number, but they're saying it is vertical. Okay, here 1 is the odd number, but here horizontal. So it depends. It depends on the project and the technology node you are using. So yeah, this is the vertical, some resistance and capacitance values. And thickness again, I think thickness is 0.53. Let's see how much here. It should be okay, it is this, it is same 0.53. And yeah, then via the metal to related via. So each metal should have via information also. If you don't have the via information, and if you don't drop the via, that means it is a open, right? So open means your delays may not be accurate, will not the modeling is different, right? It will not be accurate, and you will see some random delays. And yeah, that's why each metal should have the via information also. And metal 3, see, metal 3 is like the width is 0.28. I think it should be the same like metal 2 only, 0.28. This values we don't control, guys. This information will be given by the foundry. So in which you targets the certain process nodes, right? Like say 2 nanometer, 3 nanometer, whatever. So and the based on that it will be vary actually. The foundry guys, they will give these numbers. You can't change simply. Okay, you should follow them. Okay, and direction here horizontal, again it's a odd number horizontal. And the pitch, spacing, resistance, again it's same. And the thickness, and yeah, it's the same. And again metal 3 via information like this. Yeah, it's gone like that. Yeah, let's see how many metals are like 4, 5, go down. Yeah, metal. Oh, okay, this is also okay. It has the macro related information also. It's I told you, right, it's a merged. I merged everything inside this, like a tech left and the seller macro left. See, this is the macro. Oh, I think macro class should be core. Okay, guys, remember this. Okay, this will be a interview question. It's like some people doesn't know like how tool identify the macros and standard cells. We'll see again what class for standard cell. But the macro class is the core. If the tool sees the class attribute as core, then it will consider as a macro. Okay, macro. Then this is a macro name, and yeah, we just seen the origin. Okay, the origin, the size of the macro, see symmetry of the macro, and side and the direction. Macros will have the directions also, no? And the in out means the that is a bidirectional pin, I think. And the port information, okay, and it is ended here. So basically, you should able to tell macro like origin, class, origin, size, symmetry. At least these 4 points you should tell. I mean, no one will expect you to tell everything. It's just a left file. Like we don't see regularly, we don't see this file, right? Just for our understanding only, we will check this file. So no one will expect you to tell everything. Just some points, some basic like class. One of the important point in like how do you identify? How does tool identify the whether the cell is macro or is a normal standard cells? So you should be able to tell this point. If the attribute given as a core, it will be a macro, and the origin, the size, symmetry. Yeah. Okay, and these are macros, and I think metals, maybe metals, some maybe metal 14 or 15. I don't know. Let me check here. Metal. Okay, next is metal 1 6. See metal 4 also. I think maybe metal till metal 6 only here they have this file. I think yeah. So we have seen the macro information, and let's see if we have any cell information here. But yeah, cell is nothing but yeah, I think they don't specify the cell. I think macro is nothing but a kind of cell only. The cell will also have the class and the origin and the size. Maybe class it should be block. Let me check block. Okay, we don't have. I think we don't have that information, but yeah, macros and cell in the information is the same: class, origin, size, and symmetry. Okay, guys, and the metal is like metal will have the direction, pitch, width, resistance, capacitance, thickness, and vias will have via is also like the antenna related information, width, spacing. Okay, then let's close this file. So hope you understand. All of you understand this left concept.
Yes, sir.
Okay, now let's check the netlist. Okay, so what we discussed in the netlist here, let's see. Okay, input and output information of the design, wire information, cell instance information, module information, hierarchy information, and the port information. Let's see that we have that information here or not. Okay, module information. Module is defined as some ARB module. Okay, okay, some ARB module, and it has some pins, reset pins, clock pin, some different kinds of pin of this module, and they defined here the P underscore read is the input pin, and output is like some ROM data. This is some outputs, and P adders again it's a bus actually 0 to 8 means this is a bus. I mean P adders 1, P adders 2, 0 to 8 like that, and yeah, input, output, and the wire information also. Okay, and this is one more cell. This is the instance. Okay, the instance this has these. Okay, I think we are cloning here. Maybe let's see. This is the instance. This is the cell. The module. They define one cell like this. in the netlist, everything will be with the module only. They will start defining cell details with the module, okay, in the netlist. So I don't want you to be expert in this, but on basic, I want you to understand some basics, okay? Because this netlist you will not this netlist will not be written by us. It is written by some front end guys, and okay. So, but at least you should, if you open the netlist, you should understand, okay, they define some cell here, and it has some ports like this, and they also define here, okay, the reset is the input pin, and also clock is the input pin, and output is, okay, ROM data is this is the output pin, I think. So you should able to understand like that. Okay, period is input, and again these are DMA P request. This is the input. Yeah, all this they written, and wire information, maybe present state, some maybe wire name, I think. And next, they cloned some instances with that using cell names, like the instance name they given as a CAN, and the clock and Q pin and A pin, and it mapped to this original pin from here. Okay, the clock pin, this one they mapped. They did some mapping here, and again some more cell, some buffer. PUF means some buffer related, and they given some name to this, and the buffer having two pins, na? Input A and output Y, and they map to some BG scan out. I think it should be in here. BG scan out. This is the actual cell, and these are the instances. Okay, na? We just learned, right, cell and instances information, and we also seen the module information, like module. Okay, let's see what else it is having. Then end module means the definition is closed here, and they started again one more cell. See this one, data sample mux. This is mux, and mux having these are the pins, and again they defined what is the input and what is the output, and these are the cells again. Some clock buffer and T grand. This is input A and output Y. Okay, and they define some cells here, and end module again, and one more module started. So each, like in your if you open any Verilog, also any netlist, Verilog or netlist, they will start with module, some name, okay, module name, and they will define some cells, okay, define cell, and they'll use that. They'll create some instances again here. They'll use the cells and create the instances. So everything will be like this only. Then end module. Okay, it will be like this only, module, and they will define the cells and create some instances, and they will end that module. That's it. This is the Verilog. And again, yeah, it's same. I think it should be the same. Okay, yeah, some logic they have. Okay, let's close this, and let's see the libs. This is the library file. Okay, so library, what we discussed, library will have the timing information, and functionality of cell, and input delays and output delays. Where here we discussed the library. Yeah. Some PVT conditions, power, leakage power and internal power. Let's see, do we have that information here or not? Think some operation conditions. See here, the voltages, and fast means the high voltages. See process and temperature, voltage. Some, these are all some PVT related information. Okay, norm voltage. Yeah. And let's see the timing information. Let me find some best example. Uh, yeah, I think this one. So this is the lookup table. So I think it will read in a different format, but this is the input we get from the foundry. This is the foundry given input only. Some, I think this is some technology node is different. Let me see. I think they mentioned here. I don't see they mentioned the technology node in the library. I think let me check somewhere. Uh, I don't see anywhere. Maybe we try checking the left. Okay, this one is the left. Maybe I think this is 18 nanometer. I think TSMC related TSMC left file. This is okay. 18 nanometer. I think we close this. Yeah, and let's go back to the lookup table. Okay, this is the lookup table. So the tool will check the tran, like max tran and max cap max cap value, and it will pick some randomly some delay value. So don't go for much details. So just have a basic understanding that cell delay depends on the input tran and output load, and based on that the cell delays will be decided, and that cell delays we get from the library. Okay, that information is good enough. Okay, and yeah, I think it should be fine. It will be the same everything like this one. It will, all cells will have this kind of lookup tables. Okay, some leakage power, some leakage power. Yeah, this is some pin information, the direction, the pins, cell pin, the cell capacitance, what is the capacitance of cell, and these are some timing information, delay. Okay. Yeah, is everyone clear with this?
Yes.
I think we are already crossed the time, but yeah, I covered today all the inputs, and one more input is like UPF. I think this UPF is we don't need because UPF is like low power design. Let's say low power is like this is your partition, and okay, and some module, some logic is sitting here, and some logic sitting here, somewhere here, and this module is related to some, let's say, power button, our mobile power button. Let's say, okay, this is our power button, and this is our some maybe some WhatsApp notification related. Okay, WhatsApp notification. Let's say, just assume notification related functionality is sitting here, and power button. So UPF, what they define, like they will that in this UPF they define power domains. Okay, power domains. This is advanced topic actually. So power domains, like when should be this logic should get turned on, and when logic should get turned off. So that kind of information. So let's say power button, you like you don't need to turn, or you don't need to supply the power to this logic every time, right? So you need, whenever you click it, like if you click the power button, you should turn on, and click the power button, you should go off, right? So that's why, like maybe they will put this logic in a switchable domain, switchable or gated domain. We also call gated domain or switchable domain. Uh, this terminology is important, guys. Try to understand. Switchable. Switchable means like it's a switcher, turn off and on, off and on. Gated also, like it's off and on. Whenever we need it, we turn it. We don't. Whenever we don't need, we will turn off it. Okay, so that will save the power. And what's like, let's say you turn off the mobile now, and let's say someone messaged you, so that message should come, right? It's not like when you turn on, like it will, the mobile should be always, it will be on the standby mode. So even though if someone message you, it should come and save in your WhatsApp, right? So maybe this, they will put this domain in a always on domain or ungated domain, always. Okay, always on domain. That means this logic should be on every time, or else ungated domain, ungated. So this kind of information UPF will have, like power domains and power switches, and yeah, and later we need to, you will create some voltage areas, and voltage area nothing but like power domains will have the logical information, like what kind of logic information, but you don't see it physically. To see physically, you will create the voltage areas, also we call as islands, or voltage. This is voltage area. So this kind of information UPF will have. That is one more uh, input. But this input is whenever your design is the low power design. So no need to be all designs is a low power designs, like in automobiles. Why they don't need low power designs, right? They don't. That's why, I mean, if you are working on a automobile projects, or networking related projects, if you are working on network relating chips, so maybe they don't have this UPF. They don't need to use this kind of uh, arrangements, like the power shed and power on. They don't need it. It's they will have the single power domain, and that power domain supply the current. I mean the current every time power. So yeah, this is one more input, guys. UPF. So, but this is not a basic input. The basic inputs is like netlist, libraries, lefts, and SDC. Those are the 4 basic inputs.